This is your presenter Asloob Mudassar, and I am presenting slide number 67 of the course on laser physics. Question is, discuss electronic states in a bulk semiconductor. The answer is, in a bulk semiconductor crystal, the dimensions of the crystal structure are much larger than the de Broglie wavelength of electrons under consideration. The outer electrons of the atoms of a semiconductor material are delocalized over the whole crystal. The corresponding wave function can be written as block wave function. Psi of r is equal to uk of r multiplied by e to the power iota k dot r. uk of r has the periodicity of the crystalline lattice. Solving Schrödinger wave equation for psi of r reveals that number 1, eigenvalues of the electron energy E are functions of k. Second is that eigenenergies E fall within the allowed bands. We consider two bands, valence band, which is the highest field band, the conduction band, band higher to the valence band. E and K relationship can be approximated by a parabola shown in figure 67.1. So let me show you first this figure. The caption of the figure is energy versus K relationship for a bulk semiconductor. So we are plotting the energy. For example, for the conduction band, we are plotting the energy along the vertical axis, and for the valence band, we are plotting the energy down the vertical axis. So EC is the energy of an electron along the conduction band, and EV is the energy of the electron in the valence band. So you see that you can see filled circles in the valence band, and you can see empty circuits or the hollow circles in the conduction band. These are actually the available states. The electrons, for example, in the valence band could be in any of these states, and similarly when excited, the electron can go to any of the states available in the conduction band. So these are the available states in the valence band and the conduction band. EG is actually the gap between these two bands. And K, you see that we have a plotted K along the horizontal axis, and we have a plotted EC, that is the energy of an electron in the conduction band along the positive y direction, and we have a plotted the electron energy in the valence band down the vertical axis. So you see that there is EC may start from the bottom of conduction band, and the valence band may start from the top of the valence band. That is, the EV may start from the top of valence band, and EC may start from the bottom of the conduction band. But you see that these could be different references. We have to set the same reference for both the energies. That is the same reference for EC and the same reference for EV. Usually we choose the reference to be the top of the valence band. For example, this point. So this that is the top of the valence band can be chosen as the reference. Then the EC, that is the conduction energy, that is the electron energy in the conduction band, will then be equal to the energy in the energy gap, that is EG, plus the energy in the conduction band. So these will be discussed also in the text. So E and K relationship can be approximated by a parabola shown in figure question 67.1, which I have just shown. EG is the energy band gap, EC starts from the top of EG, and EV starts from the bottom of EG. Energy of the electron in the conduction band EC is given by. So you see that here, according to this description, the EC will originate from the bottom of the conduction band and EV will originate from the top of the valence band. So up till now this is true, but in the next we shall modify it. That is, here there are two references. EC has a reference which is at the bottom of the conduction band, and EV has a reference which is at the top of the valence band. But these are two references, but we shall later on set a single reference for these two energies. Okay, the energy of the electron in the conduction band denoted by EC is given by, so this EC, that is the energy of an electron in the conduction band, is given by h bar square k square over 2 mc, as given in equation number 67.1, where mc is the effective mass of the electron at the bottom of the conduction band and is given by. So the mass of the electron, the effective mass of the electron at the bottom of the conduction band is given by equation number 2, which is mc is equal to h bar square over double derivative of d square of ec over dk square evaluated at k is equal to 0. So when say k is equal to 0, it means that we are talking about the bottom of the conduction band, because at the bottom of the conduction band, from here you can see that k is equal to 0 only at the bottom of the conduction band. So mc, that is the effective mass of the electron, has been defined at the bottom of the conduction band. So mc is equal to h bar square over d square ec over dk square evaluated at k is equal to 0. And you see that we have EC is available from equation number 67.1. We can take the double derivative of this equation with respect to k, and then we can find the mass of the mc, that is the mass of the electron, effective mass of the electron at the bottom of the conduction band. Similarly, the energy of an electron in the valence band measured from the top of the band is given by, that is the EV is equal to h bar square k square over 2 mv. So this energy has been measured from the top of the valence band, where mv is the effective mass of the electron at the top of the valence band, again where k is equal to 0. That is this point where k is equal to 0 and the curve is and the parabola is touching the k axis. So this is the point where we have the reference, and the mass of the electron in the valence band is measured at this point. So where mv is the effective mass of the electron at the top of the valence band and is given by mv is equal to h bar square over double derivative of ev with respect to k, that is a d square ev over dk square evaluated at k is equal to 0, as shown in equation number 4. When dealing with a transition, it is appropriate to refer the energy to the same reference level. So you see that here, as I previously said, that we have two references over here. That is, for EC we have the energy, we have the reference at the bottom of the conduction band, and for EV we have the reference at the top of the valence band. So when dealing with a transition, it is appropriate to refer the energy to the same reference level. Let's choose the top of the valence band as the reference level. According to this reference, the new energies are given by, that is the energy of the electron in the conduction band, that is a new energy according to the new reference is EC prime, which is equal to EG plus EC, and EV prime, that is in the valence band, that will be equal to minus EV, because we have set the same reference for that one. According to that one, the energy is positive. When measured from the top of the valence band to upward, the energy will be taken as a positive, and from the top of the valence band downward, the energy will be measured as negative. So that's why according to that one, we have EC prime, that is the energy of the electron in the conduction band, is equal to EG plus EC, and the energy of the electron in the valence band is EV prime is equal to minus EV. This 1D model can be generalized to 3D if kx, ky and kz are the components of k. The energy equation will not change except k is given by. So these energy equations, that is equation number 3, that is EV energy relationship, and the energy relationship given in equation number 1, that is EC energy relationship. These two equations will remain the same, except that K will be changed according to equation number 7, that is K is equal to the square root of Kx square plus Ky square plus Kz square, if we are talking about the energy in 3D. Suppose that the semiconductor crystal is in the form of a parallelepiped. So we are now considering the semiconductor crystal in the form of a parallelepiped with the dimensions Lx along the x direction, Ly along the y direction, and Lz is the dimension of the parallelepiped along the z direction. Let's impose the boundary conditions that the total phase shift K dot R across the crystal is some integer multiple of 2 pi. So mathematically we can write Ki is equal to 2 pi over Li into L into small l. This small l is an integer. So move this capital I at the bottom towards left hand side, then we have Ki into Li, and then on the right hand side we shall have 2 pi into L. So integer multiple of 2 pi, and you know that Ki and Li have the same direction. So the dot product of Ki dot Li will be equal to Ki into Li into cos of 0. Cos of 0 is 1, so we have Ki is equal to Ki into Li is equal to 2 pi into L. Small l is an integer, and if you take the value of K, you have as given in equation number 8, you can write Ki is equal to 2 pi over Li into small l. This small l is actually an integer. So you see that for Ki, since I have 3 possible values, I will stand for 3 values, that is x, y, and z. Then you will have Kx, which will be equal to 2 pi over Lx into L, and then we have Ky, and then we have Kz, where I is equal to x into comma y comma z, and L is an integer and specifies the nth state. So you see that if L is equal to 0, then we shall have the initial state. If L is equal to 1, then we have the next state. If L is equal to 2, we have the next state. So if we have only L over here, we can say that it specifies the nth state. Available states have been denoted by the filled circles in the valence band and by the open circles in the conduction band. So you see that these are the available states, filled circles and the open circles. Filled circles in the valence band and the open circles in the conduction band. We have only just used these as filled and empty circles, but you see that these are more or less the same things. Available states, these are the available states in the valence band and in the conduction band respectively. Only the filled circle and the empty circle or the hollow circle doesn't, these two terms do not carry any further information, but just only a way of indicating the available states in these two bands. Okay. To understand the existence of valence and conduction band, we consider an example of the sodium crystal. A sodium atom has 11 electrons, out of which 10 electrons screen the nuclear charge, producing an effective of +1e charge of the nucleus as seen by the outermost electron. So you see that the nucleus has the same charge as that, the number of electrons around that one. Since there are 11 electrons, so the nucleus will have a charge of +11e. But you see that the 10 electrons around the nucleus will screen out the nuclear charge, and the nucleus charge will appear to be +1e to the outermost electron, or we can say that to the valence electron. So let E1 and E2 are the energies of this valence electron in the ground state and in the first excited state, with the corresponding wave functions represented by psi1 and psi2. So you see that here for the valence electron of the sodium atom, which is only the 1 electron in the outermost shell, we are assuming that it is when the sodium atom is in the ground state, it has an energy E1. But if you move the sodium atom to the next excited state, then it will have an energy E2 with the corresponding wave functions psi1 and psi2. If two such sodium atoms are separated by a distance d much larger than the atomic dimensions, the two atoms do not interact with each other. And if the two atoms are in energy state E1, then this level will be doubly generated. So you see that here I have said that you have two sodium atoms. The sodium atoms are well separated from each other so that they do not interact with each other. Then each atom is in the energy state E1. So the two atoms, each of them is in energy state E1. This is what we say that the level E1 is doubly generated. That is, we have single level, we have two levels, that is E1 two times with the same energy. So this is the doubly generated energy levels. So we can say that the level E1 is doubly generated. That is, the two particles have the same energy. The overall wave function will be the combination of the two wave functions psi1a plus psi1b. So you see that psi1a is actually the wave function corresponding to the ground state of a particle of a sodium atom, of the electron in the sodium atom, and psi2 is the wave function corresponding to the first excited states. So here we are writing A for atom A and B for atom B, since we are considering two atoms over here. So psi1a is actually the wave function of atom A in state 1, and psi1b is the wave function of the atom B in state 1. That is, the both atoms are in the ground state. So the combination of the two wave functions psi1a and psi1b either in phase or out of phase by 180 degree. So when we have the two wave functions, both atoms are in ground state with the wave functions psi1a and psi1b, then there is two possibilities. That is, the wave functions have the same phase, or the wave functions have a phase which are 180 degree out of phase. So under these two conditions, we can write the two wave functions as shown in figure 67.2. The caption of the figure is addition of wave functions of two identical atoms in symmetric and anti-symmetric cases. So on the leftmost we shall get the symmetric case, in which we have the addition of psi1a plus psi1b with a positive sign. This positive sign means that both the wave functions, that is the psi1a and psi1b, are in phase, and we are simply adding them together. The wave function, the shapes of the wave functions are shown over here. So you see that there is a difference d between the two atoms. We have shown these atoms by small dots on the horizontal axis, and d is the separation between atoms. So each atom has a wave function, but you see that the d distance is such that the wave functions are overlapping with each other. You can see that the dotted line, above the dotted lines, the two functions are overlapping with each other, and this overlap is in phase. That is, we can say that the two atoms are in symmetric form. So this is the addition of the wave functions of two identical atoms in symmetric form. Now consider another case on the right hand side, anti-symmetric wave functions. So you see that the one wave function, that is psi1a, is along the vertical directions upward, whereas psi1b is 180 degree shifted and is in the downward direction. You can see the full wave functions shown as dotted lines, and you know that under the dotted lines the wave functions will overlap together and will add like the one as we have shown. But you see that here this is the case where the wave function of the atom B is 180 degree out of phase with respect to atom A. So the addition will be psi of 1a minus psi 1b. So this negative sign indicates that the wave function of the atom B is 180 degree out of phase with respect to the wave function of atom A. So we have shown the symmetric wave function and we have shown the anti-symmetric wave function. Okay, the addition of two wave functions in phase corresponds to symmetric case, whereas the addition in out of phase by 180 degree corresponds to the anti-symmetric case as shown in the figure, which I have explained. Now you see that we started the game with only two sodium atoms, and you see that this is a separation between the two sodium atoms. The sodium atom, the two atoms may have same phases or may have a phase of one with respect to other by out of phase by 180 degree. So we have the two possibilities, that is the symmetric wave functions or the anti-symmetric wave functions. That is, the two wave functions can simply add or can simply subtract. When the atomic separation becomes sufficiently small, then due to the interaction, doubly degenerate levels are split into two levels. So again read, this is important. When the atomic separation becomes sufficiently small, then due to the interaction, doubly degenerate levels are split into two levels. You see that before that, when the separation is large, then both of these will have the same energy. That is the two levels. That is, the atoms are, you see that we have two atoms and both atoms are in the same level with the same energy E1. So both atoms are having energy E1 and E1. That is, both are in the ground states. But you know that when these two atoms are brought closer to each other, then there will be an interaction between them, and the degeneracy of the levels is shifted. That is, there is a shift of energy. That is, the two will have different energies. Thus, if they are, so the two atoms will have different energies when they are brought closer to each other. Thus, if there are n atoms with close enough interaction, the n degenerate E1 levels are split into n closely spaced levels. So you see that if you have n atoms, n sodium atoms, which are very close to each other, such that they are interacting with each other, then the degeneracy of the levels E1 is lifted. That is, now the sodium atoms, which are now very close to each other, each will not have the energy E1, but will have different energies, although they are very closely lying with respect to each other. So the n degenerate E1 levels are split into n closely spaced levels, and these closely spaced levels of course will have closely spaced energies. So this is what I have given an example of the sodium atom. So many sodium atoms, for example n sodium atoms, so n closely spaced levels. Now the state of E1 levels thus gives rise to the valence band, because E1 corresponds to the ground state of the sodium atom. So all the levels, when the sodium atoms get together or are brought closer to each other, then you see that due to that interaction, then the levels will be split closely, and then of course the energies will be different. The state of E1 levels thus give rise to valence band, and the state of E2 levels give rise to conduction band. Each band thus consists of n closely spaced levels. So you see that this is what I have described, that how the valence band is formed. So this valence band, which is this E1 is actually the E1 is, you see that only a single level. And this single level is possible when all the n atoms of the sodium, all the sodium n atoms are well separated from each other. That is, there is no interaction between them. But you know that when these n sodium atoms are brought together, then this single level is split into n levels. So you see that these are n levels on the left hand side of the single level E1. And you see that if the atom if this is energy E1, which corresponds to the ground state energy of the sodium atom, then you see that this band will be called the valence band. You see that the energy, we have plotted the energy D over here. If D is larger, then all these bands will start converging closer to each other, and ultimately they will come out to be a single level. when D is very large. But when D becomes smaller and smaller, then you see that the splitting of the level E1 into many levels will starts, and these many levels are then be well separated from each other for much smaller value of D. So if the sodium atom is now in the excited state, that is, you have, for example, n sodium atoms, and if you excite them to level E2, so then the level E2, and in the level E2, if these excited sodium atoms are brought closer to each other, then you see that the atoms which had the energy E2 being isolated from each other, now their energy levels, they will split into closely spaced energy levels. And this closely spacing will increase, that is, the spacing between these levels will increase with a smaller value of D. So you see that a conduction band is formed for the excited states of the sodium atoms when they are very close to each other and when they are interacting with each other. So we have the conduction band, and similarly when all the sodium atoms are in the ground state, we have the valence band. So you see that when the mixture is closed, that is, we have all the atoms, sodium atoms in the crystal very close to each other, then of course their ground state level will be split into many levels in the form of a band, which we call the valence band, and the excited state will also be split into many levels, forming a conduction band. And you see that if the number is infinite, which of course is the real case in case of crystals or in case of semiconductors, then you see that, and of course the D is very small for such elements, for such semiconductor materials, then you see that this overlapping will be so small that you will find a complete band of levels, band of energies, both for the valence band and both for the conduction band. So you see that this is the plot of energy E along the vertical axis, and the distance, that is the separation D between the two atoms or between the many atoms, is plotted on the horizontal axis. In a semiconductor crystal, N is usually very large, and the individual energy levels in each band are not resolvable as shown in figure 67.3. So you see that in this figure you can see that these energy levels which have been split into many closely spaced energy levels, you can resolve them. But if the number is very large, as in case of semiconductor, and is usually very large, then these levels are so closely lying with respect to each other that you cannot resolve them, and it appears to be a continuous energy band in case of semiconductor. Okay, within the parabolic band approximation, the electrons is then considered to be free particles of a momentum P is equal to h bar k, which in 3D takes the form P vector is equal to h bar into k vector. So let me read this statement, because this statement is very important. Within the parabolic band approximation, the electron is often considered to be free particle of a momentum P is equal to h bar k, which in 3D takes the form P vector is equal to h bar k vector. So you see that here we are talking about the single electron. For example, if it is a valence electron, then you see that this electron can be considered as a free particle. And that free particle in the semiconductor, for example, or maybe for example in the sodium crystal, may be considered to have a momentum which is given by P is equal to h bar k if the particle is moving along one direction. But if the particle can move in any three dimensions in 3D, then you see that we have the vector, that is the P vector, momentum vector, will be equal to h bar times the k vector. Okay. So you see that this is the cone of energies that is generated, and if you look this cone of energies from the E2 level, from the E2 facing towards this cone, that is your eyes are placed at E2, you will see that this cone of energy appears to be a parabolic. And similarly from E1, if you look on the left hand side, that is towards the valence band, then of course this appears to be a parabolic form. And you see that we have, if you have K, for example, some reference with respect to that K, if you set K value along the E2 axis, then you have value, then you have K increasing along the upward direction and K is decreasing, that is K becomes negative along the minus E energy direction. And similarly for the valence band, if you take K along the, if you take K as a reference, that is K is equal to 0 along the E1 direction, along the E1 axis, then you see that K will increase along the upward direction towards E, and K will have a negative values on the other side, that is along the negative side of the energy axis. For example, over here, what is the caption? Heavy hole represented by HH, light hole represented by LH, and split of valence bands for unconstrained 3 to 5 semiconductors. From group number 3 to group number 5 semiconductors, for these semiconductors lying in these groups, we may have valence bands in the form of heavy hole, in the form of light hole, in the form of split of valence bands. But we have shown all these three valence bands together so that we can explain them. But you see that in this group of semiconductors, only one of the bands will be important. The most important band will be HH band. This is what we shall explain over here. But you see that all the three bands, that is the HH band, LH band, and the split of bands, all these are the valence bands. But you know that there is no splitting in case of conduction band, only one conduction band is there. And you see that we have set the reference at the top of the valence band, where we have the K axis. And you see that above this K axis, which is at the which we have fitted at the top of the valence band, above that we have some energy gap, and then we have the conduction band. So this is our reference. So we have set our energy reference at the top of the valence bands. And these are three valence bands we have shown, but only one of the valence bands will be more important, as we shall see, and that will be the HH band. So you see that we have the K wave number there, that is what we have plotted. The value of K number is 0 at the center. The K is positive along the right hand side, and K is negative along towards the left hand side. So we have the parabola over here, that is the energy is lying in the form of parabolas. And if you set the K axis along the E2 axis, then above, then the energies along the positive direction and along the energies along the negative direction when viewed from the reference axis which is passing through the E2 axis, you will see that these energies will appear to be parabola, and similarly for the case of the valence band. So that's why we have plotted them in the form of a parabolas when we have a K number. You see that K is actually 2 pi over lambda, the wave number. And the 1 over lambda can be written as nu over C. So we can write K is equal to 2 pi into nu over C, where nu is the frequency of the photon. So you see that we are plotting the photon, that is the energy of the photon. If you go along increasing value of K, it means that you are also increasing the value of nu. And when the value of nu is increased, it means that the value of the energy is also increased, as E is given by E is equal to h nu. So if you increase K, you increase nu, you increase E. So that's why the parabola is upward over there. And you see that the parabola is downward over here for the valence band. Because for the valence band, these are the more, you see that more you can say that more bound electrons. So the electrons will be more bound because we have the negative energies for them. But for the conduction band, we have the positive energies, because our energy reference is at the K is equal to 0 level. where the energies above this k axis is positive and the energy this below k axis is negative. So these negative energies shows that these electrons are strongly bound electrons in the valence band, whereas the electrons can move when in the conduction band they can be treated as the free electrons. We can also treat the electrons within the valence band as the free electrons having the energy P is equal to h bar k, and in the 3D the energy will be given by P vector is equal to h bar into k vector. So let's read the text. Direct band gap materials. So there are some materials, semiconductor materials, which are called direct band gap materials, and these are the gallium arsenide, indium gallium arsenide, aluminium gallium arsenide, etc., where the top of the valence band and the bottom of the conduction band occur at the same k value. You see that k is equal to 0 over here at the top of the valence band, and k is also 0 for the conduction band. If you extend the center of the conduction band downward, it will meet the axis at k is equal to 0. So for those materials in which the conduction band and the valence band have the same value, for the k, have the same k value, then of course such materials are called direct band gap materials. So let me read again. Gallium arsenide, indium gallium arsenide, aluminium gallium arsenide, etc., where the top of the valence band and the bottom of the conduction band occur at the same k. In this case, you see that k is equal to 0 we have. At the same k value are important laser materials. Semiconductors in 3 to 5 group have 3 different types of valence bands. Heavy hole represented by HH, light hole represented by LH, split off. So these are the 3 valence bands. It is because the individual atoms in the lower state have p symmetry, and the 3 valence bands originate from a suitable combination of the px, py and pz orbitals, keeping in view the crystal's symmetry. So you see that 3 possible orbitals are possible for these electrons. Electrons could be in px, py and pz orbitals, and combining due to the combination of these orbitals we can have these 3 bands, HH band, LH band and split off band. But you know that there is no such orbitals available for the conduction band. Let's see next. There is only one conduction band because the individual atoms in the excited state have spherical symmetry like that of the S state atomic orbital. You see that the S state atomic orbital is spherical in shape, and each atom in the conduction band has a similar symmetry, spherical symmetry, and due to that one the conduction band has only one conduction band, because the individual atoms in the excited state have only one spherical symmetry. But you know that this is not the case for the valence band, where we have px, py and pz orbitals. The split of a band is slightly lower in energy due to spin orbit coupling. Spin orbit coupling means that the angular momentum of the spin of the electron spin and the angular momentum of the orbital spin, these two spin magnetic quantum numbers or magnetic moments interact with each other. That is, the spin magnetic moment and the orbital magnetic moment interact with each other, and result in the form of spin orbit interactions. The split band is slightly lower in energy due to spin orbital interactions. The magnitude of this energy is much larger than kT, and thus the band is always filled with electrons. The split off band does not appropriate in any type of radiative and non-radiative transitions, because the band is completely filled. Light hole valence band makes a little contribution to these transitions. HH band is thus considered effectively as the valence band. So you see that out of these three bands we have declared that HH band is actually the valence band from which the transitions can easily take place. The transitions from the LH band are very small in quantity and can be ignored, whereas now no such transitions are possible from the split off band. So we shall only be considering the HH band. Next we calculate the number of energy states represented by P of k when ranges from 0 to k, where k can take both positive and negative values. So you see that the energy of states represented by P of k is given by 2 multiplied by the volume of sphere of radius k divided by the volume of the unit cell. So the volume of the sphere is 4 pi over 3 into k cube, because we are now about talking about the k space. So we are talking about the volume of the sphere in k space, where because you see that k is equal to 0 in the center of the sphere and k will increase positively if you place that sphere at the origin of the xy coordinate, xyz coordinate, then you see that k will be positive along the positive x axis, along the positive y axis, along the positive z axis, and on the other axis, that's along the minus x direction, minus y direction, minus z direction, it could be negative. So we are taking over P of x, the density of states, that is the number of energy states P of k is equal to 2 into volume of the sphere of radius k divided by the volume of the unit cell. So the volume of the sphere is 4 pi over 3 into k cube, and the volume of unit cell in k space is 2 pi over lx, at 2 pi over ly, 2 pi over lz. Actually this 2 pi over lx is actually kx for the parallelepiped having lx dimension, and 2 pi over ly is actually ky, which is actually the parallelepiped having ly as the dimension along the y axis. And similarly 2 pi over lz is actually kz, which is equal to 2 pi over lz, and lz is the dimension of the parallelepiped along the z direction. So you see that multiplying all these quantities and introducing that the volume is equal to lx into ly into lz, we can write the P of k, that is the number of energy states, is equal to k3 multiplied by the volume of the parallelepiped divided by the 3 pi square, as shown in equation number 9. V is equal to Lx into Ly into Lz is the volume of the crystal. The factor 2 accounts for the two states arising from the electron spin. That is, the electron spin may have two possibilities. So due to that the two possibilities, we have a factor of 2 there, because two energy values will be possible for the spin up and for the spin down. So due to that one, we have multiplied by the 2 so that we can count all the energy states. The density of the states per unit volume, which we represent as rho of k, is given by. So the formula of rho of k, rho, that is the density of states, can be obtained from the formula of the number of energy states P of k through the formula, that is rho is equal to 1 over V and the dP over dk. So if you take the derivative of P over here with respect to k, you will get k square over pi square, and introducing the value of V, which is equal to Lx into Ly into Z, is Lz. So this rho is actually the density of states, that is the density of states per unit volume. Rho is given by equation number 10 is equal to k square over pi square. Equation number 9 and equation number 10. This is equation number 9, this is equation number 10. Both are valid for the valence and conduction bands. Equation number 10, which is over here, can also be expressed in terms of the electron energy using the relationship. So you see that we can now express that these relationship in terms of the electron energy. Rho of EI, you know that is the energy. I stands for, I has two possibilities. that is for the valence band or for the conduction band. So EI has though this equation, which is the equation number 11, are actually two equations. One is equation for the valence band, the other equation for the conduction band, but both equations are identical. So for the valence band you will have rho of EV multiplied by DEV is equal to rho of KV multiplied by DKV. For the conduction band you can replace I by C, and this equation can then be written for the conduction band. So this is the density of states having energy in the range from EI to for this total states on the left hand side, that this is the density of states having electrons with the energies EI to EI plus DI. And on the right hand side we states that this represents the density of states with the wave number k having values in the range of Ki to Ki plus Dki. So these two quantities are of course related with each other through this formula as shown in equation number 11. You can find out the value of rho of EI by moving other factors on the other side, or simply you can take the derivative with respect to DEV for example. So we are writing this equation in equation number 11 for the case of the valence band, and this is shown in equation number 12. So this is for the valence band. Now we can put the value of dk over DEV from equation number 3. So let me show you equation number 3. This is equation number 3. You can take the value of EV from equation number 3, or you can also take the value of K from equation number 3. And then you can use these values in this equation, that is dk over DEV, that is the derivative can be calculated with respect to EV using that equation, that is from equation number 3, and we can also eliminate K using the same equation. Then we obtain that is the rho of EV is equal to 1 over 2 pi square into 2 mv divided by h bar square whole raised to power 3 by 2, and then EV raised to power half as shown in equation number 13. So you see that this is what we can calculate the energy, or that is the density of state at a given energy EV. And this energy is, you see that the energy of the electron in the valence band. And we can also obtain a similar relationship for the conduction band. So the density of states, that is the density of states for the energy EC, that is for the electron having energy EC, the density of such states is given by 1 over 2 pi square, and then the rest of the quantities are similar to this equation, except that we have replaced V, which stood for the valence band, replaced by C, which stands for the conduction band. So we have explained equation number 13 and equation number 13 respectively for the valence band and for the conduction band. For 3 to 5 groups compounds, MC is much less than MV. You see that we have declared that MC is actually the effective mass of the electron in the at the bottom of the conduction band, and MV is actually the effective mass of the electron at the top of the valence band. And MC, we have found that MC is much less than MV. Not found from here, but this is what we are taking granted from the experimental data or from detailed theoretical analysis, that MC is much less than MV, which gives that rho of EC is much less than rho EV, which means that the density of states of electron energy in the conduction band is much smaller than the density of states of electron energy in the valence band. So from here you can guess the amount of density of states available in the valence band and also in the conduction band. Now there is another relationship, that is the mass of the electron for the LH. You see that LH we have written over here. Let me show you again this diagram. LH. L stands for light, H stands for light hole, and HH stands for the heavy hole. So the masses of these two semiconductors in these two categories have this relationship, that is the mass of the electron in the light hole is much less than the mass of the electrons when we are talking about the heavy hole semiconductors, which means that the density of states of the light hole is a small fraction of that of the heavy hole semiconductors. Light holes are thus in great minority, and their contributions to the for 3 to 5 semiconductors are negligible. That's why most of the time we discuss the semiconductors with the heavy hole. So this is the end of slide number 67.